Today, let us know about force on a current carrying conductor in a magnetic field. The magnetic field is produced due to the flow of an electric current through the conductor. Hence, force is exerted by a magnetic field on a magnet which is placed on the surroundings of a conductor. According to French scientist André Marie Ampère, an equal and opposite force is exerted by the magnet on the current carrying conductor. Let us do an activity to demonstrate how force, which is due to the magnet, is acting on a current carrying conductor. For this, we need a small aluminium rod AB of length 5 cm, which has to be suspended horizontally on a stand between the two connecting wires as shown. Take horseshoe magnet and place it in such a way that the rod lies between the two poles of horseshoe magnet with magnetic field directing upward. The north pole has to be vertically below and south pole has to be vertically above the aluminium rod. Connect the ends of the wire in series with the battery and the switch. Now, let the current pass through the aluminium rod from B to A. We will notice that the rod moves towards the left. When we change the direction of the current, the aluminium rod moves towards the right. Through this activity, we can conclude that the current carrying aluminium rod placed in magnetic field experiences a force. The direction of force is reversed when the flow of current is reversed. That is, the direction of force is also reversed when the direction of the current through the conductor is reversed. Secondly, if the poles of the horseshoe magnet are interchanged, then the direction of the force acting on a current carrying conductor gets reversed. This shows that the direction of the force on the conductor depends upon the direction of the current and the direction of the magnetic field. If the direction of the current is at right angle to the direction of the magnetic field, then the magnitude of force will be higher. In such condition, we can use a simple rule to find the direction of force on a conductor. In this case, the direction of the current and the direction of the magnetic field are considered to be perpendicular to each other. And from this rule, we can also notice that the direction of the force will also be perpendicular to both the direction of the magnetic field and the direction of the current. This rule is known as Fleming's left-hand rule. It states that you have to stretch your thumb, forefinger and middle finger of your left hand in such a way that all the three fingers are mutually perpendicular to one another. Then the forefinger shows the direction of the magnetic field and the middle finger shows the direction of the current. Then thumb shows the direction of the force acting on a conductor. So, The thumb shows the direction of the force acting on a conductor, then forefinger shows the direction of the magnetic field, and the middle finger shows the direction of the current. Very simple, isn't it, children? And now we have electric motors, electric generators, loudspeakers, microphones, and measuring instruments are few devices that use the current carrying conductor and magnetic field. When we just switch on the switch, an electric current starts running, immediately the fan rotates. It's because of a device which converts electrical energy into mechanical energy. Such type of device is known as electric motor. These electric motors have wide applications like washing machines, drilling machines, electric cars, etc. You may be thinking how the flow of electricity, that is mainly the movement of the electrons, can make the blades of the fan rotate. The secret of these motors are magnets. Already we know that current carrying conductor experiences a force in presence of magnetic field. The electric motor works on this principle, that is, current carrying conductor experiences a force in presence of a magnetic field. This force is used by electric motor to spin the current carrying conductor. Let us understand this in detail now. First, we will consider a strong magnetic poles, that is North Pole and South Pole, which produce a magnetic field around it. Now consider a current carrying rectangular coil between the magnetic poles. We will consider the battery little later after understanding the concept better. Remember, each side of a rectangular coil behaves as a current carrying conductor in presence of magnetic field. Each side of a rectangular coil experiences different force. Because of this force, the rectangular coil rotates. In order to find out the moment of the rectangular coil, we need to know the direction of the force along each side of a rectangular coil. So, in order to find out the direction of the force, we need to apply Fleming's left-hand rule. It states that after stretching the thumb, forefinger, and middle finger of your left hand such that they are mutually perpendicular to each other. If the forefinger points in the direction of the magnetic field, then the middle finger will be in the direction of current, then automatically the thumb will point in the direction of force. If we need to find out the direction of the force of the pink wire, then arrange your left hand, that is forefinger, middle finger, in the direction of magnetic field and current. Then the thumb is showing the direction upward. If we apply the same rule for the blue wire, then the thumb shows the direction downward. That is, the blue wire experiences force downwards. If we consider yellow wire, then observe the direction of current and magnetic field are parallel to one another. Already we have studied the fact that wherever the magnetic field and the current are parallel to each other, they do not experience any force. Similarly, this yellow wire too does not experience any force as current and magnetic field are parallel to one another. For example, if we take a rectangular boat similar to that of rectangular coil, this left side experiences upward force and the right side experiences a downward force. Then the board will move like this, that is, spinning in the clockwise direction. So I can say that the rectangular coil experiences force only through the pink and the blue wire. Therefore, the rectangular coil will rotate or spin in the clockwise direction. As it spins, the force experienced by the pink and the blue wire will remain the same because current is flowing in the same direction. Also, magnetic field is still in the same direction and the force experienced by pink wire is still upward and blue wire is still downward. But just think of yellow wire, children, now. Earlier, these wires were parallel to the direction of magnetic field, but now they make an angle with the magnetic field, so surely they are going to experience a force. These forces do not affect the rotation of the rectangular coil. Now let us see the reason behind it. If we apply the left-hand rule to this wire, then we can observe that the force is inward. Similarly, if we apply the left-hand rule on this yellow wire, then the force comes outward. If we consider the same example of a boat and pulling it, that is one inward and outward, then these forces will be equal and they are in opposite direction. Therefore, they are going to be cancelled out. Hence, net effect on the rotation or the motion of a rectangular coil by yellow wire is 0. As a result, we can totally ignore the force experienced by yellow wire on either side. Now, our coil is spinning, but there is a problem now. If we bring back our boat, I want this boat to continuously spin in the clockwise direction. Then the force acting on the right hand should always be down and the force acting on the left should always be up. If I consider our rectangular coil, once the pink wire comes to the right, notice that the force on the right side has become up and force on the left side become down. This will spin the coil back in the anti-clockwise direction. The coil will spin in the clockwise and anti-clockwise direction. If this is going to happen, the device will no longer be a motor because it is not completing a full cycle. Then how to solve this problem now? That is to make this rectangular coil to continuously spin in the clockwise direction. When the rectangular coil comes in this direction, then the force on the pink wire should be downward and that of the blue wire should be upward. Then only the rectangular coil can continuously spin in the clockwise direction. For this, we need to reverse the direction of force of these two wires. Then how do we reverse the direction of force? Let's recall the Fleming's left-hand rule. If I want to reverse the direction of the force, then the thumb should point downward, and for this we have two ways. That is, either we can change the direction of magnetic field direction, that is by reversing the direction of the forefinger, but we are not going to do so because flipping the magnetic field is not so easy. For this, we need to change the poles and it cannot be done automatically. But there is another method, that is to keep the magnetic field in the same direction and change the direction of the current. That is, change the direction of the middle finger. As a result, so the force experienced will be downward. If we change the direction of the current along all the sides of the rectangular coil, then the direction of the force can be changed. After reversing the direction of the current, the force on the pink wire will be downward and that of the force on the blue wire will be upward. And this can make our rectangular coil to spin in the clockwise direction continuously. Just observe, children. How do we change the direction of the current now? Once the blue wire comes to the right and the pink wire comes to the left, we have same problem now. Now the force on the blue wire is up and the pink wire is down. Again, we need to change the direction of the current. Once the direction of the current is changed, the direction of the force changes. As a result, the coil continues to spin in the clockwise direction. This continues till the blue wire comes to right and pink wire comes to left. Again, we have same problem. So by changing the direction of the current for every half rotation, the direction of force will change and our coil will continuously keep spinning. Finally, we have converted electricity into rotation. So, dear children, so you can see that for every half rotation, the direction of the current changes, which changes the direction of the force automatically. Now, the big question is how to change the direction of the current for every half rotation. Well, it can be done by using a device called the commutator. The commutator consists of split rings, which are basically two half metallic rings attached to carbon brushes. These brushes are just in contact with these rings and they are not connected to them. Because of the contact, the electricity starts flowing through it, and as the coil spins, notice the ring spins with them, but the brushes will stay there, so the brushes are literally brushing against the rings. This will ensure the flow of electricity through the rings. So, let's see how the split rings reverses the direction of the current for every half rotation. Right now, the pink split ring is in contact with the positive terminal of the battery and the blue split ring is in contact with the negative terminal of the battery. Yes, once the coil spins and comes to this position, now the pink ring has come in contact with this brush, that is negative terminal of the battery, and the blue ring is in contact with this brush, that is connected to positive terminal of the battery. Have you noticed, children? Due to these commutators, automatically the current will start flowing from here into this coil in the reverse direction, coming out from the negative terminal, and so the current direction changes, which will change the direction of the force. This will ensure the rotation of the coil in the clockwise direction. For every half rotation, the split rings are pressed against the brushes with the opposite terminals of the battery. For first half rotation, pink ring will press against the brush connected to positive terminal, and in second half rotation to the negative terminal. That is, we have achieved the simultaneous clockwise rotation of the coil using the commutator. What did we learn, children? We learned that the motor consists of couple of magnets and a current carrying rectangular coil. The magnetic field pushes the coil, making it to rotate. Every time as the coil comes to the position perpendicular to the magnetic field, the direction of the current will be changed by the commutator, that is, split rings pressed against the brushes. Change in the direction of the current changes the direction of the force. This will make the motor to rotate in the same direction. The commercially used motors use electromagnets in place of permanent magnet. Large number of turns of the conducting wire in the current carrying coil and soft iron core on which the coil is wound. I hope you have understood today's class, children. Hope we will meet again in the next class. Until then, take care. Goodbye.